Okay, so if you remember last week we were discussing the magnetic moment, just like in the case of the electrostatic force where we had this multiple expansion. Since the vector potential, we saw that we can write it as 1 over c j at the point r prime divided by r minus r prime dv prime. Now, if we have a j that is localized in a certain volume, so we have all these currents circling around in a finite volume whose size is, let's say, d, and for points r, so this is our origin, for points whose distance from our source is much, much larger than d, we could just expand this 1 over r minus r prime as 1 over r plus r dot r prime over r cubed plus higher order terms. And note that r prime is, the magnitude of r prime would be less than or equal to d. So this expansion, if r is much, much larger than d, will just converge very fast. So we could just keep a couple of terms in this expansion and obtain a reliable description of the vector potential. And we saw that the first term we could write it as the magnetic dipole moment. There was a mistake in our derivation on Friday, so I will just repeat that. But do you have any questions before we continue? Okay, so let's continue from here. So what we have is the vector potential. Okay, we had seen that the first term, which is the volume integral of this current density, which is basically 0, because in statics the divergence of J is 0. So just to see that, we use the identity. You see, if you have Jx, J or Ji, we can write this as del over del x, xj, xi, jj. Basically, this is correct. I mean, if you want to write the most correct thing, this would be del over del xj, xi, jj would be equal to derivative of xi with respect to xj multiplied with del j plus xi times derivative of j component of the current density with respect to xj. But this is the divergence of j, which is 0 in magnetostatics. And if you look at the first term, this derivative is nothing but the Kronecker data. It is 0 if I and j are different coordinates are independent of each other. It is 1 if I and j are equal. So if you are taking the derivative of one coordinate with respect to itself, you get 1. So this is ji. When we sum over all the j, we get the ji. So if you just take the integral of ji over the whole volume, let me put the primes, j prime meaning j evaluated at r prime. Now I can use this previous relation, del over del x j, xi, jj. Now these are all primes now. But you see, this is the integral of a total derivative, essentially. So we can write this as a surface integral. Xi prime jj prime dsj. So this is over a closed surface bounding our volume V, but our volume is infinite, and this surface is at infinity. There is no current at infinity, and hence this is 0. Well, you see, this expression over here that I use is nothing but this relation. Let's say any vector field V, integrate over volume over a given volume. This is equal to V dot ds, or in terms of its components, del over del xj of Vj dV. This is equal to Vj dsj. This is what I use in this equality over here. Now, this we had already discussed. The problem is basically with the second term. Now, let's look at that second integral. Well, we need to evaluate this integral, r dot r prime that multiplied with j prime and integrate over all volume. Now, my purpose is kind of take this r out of this integral. And when I take the r, this is a vector. So if I take it out of the integral, I would like to write this thing as r taken out. What remains, I should make an operation to obtain a vector. I should either get a number. Well, I will not be able to get a number. Other possibility, like I can write this as a vector product of some other vector. That is what I would like to do. In this form, I can take r out, but what remains is not itself a vector. So I will just mainly do some tricks to obtain a vector out of this one. Now, let's look at that term, r dot r prime j prime. In terms of components, this is a vector. Let's look at the I component of this. Well, the I component of this will be equal to integral of xj, x prime j, ji, j prime I, dv prime. This part is nothing but r dot r prime. And this is equal to xj, xj prime, ji prime. Now let us look at that, integrate over the volume. Now let us look at that term, xj prime, ji prime, d cubed v. I will do the previous trick I had, but I already know one trick that involves the j's. So let me just use that. This is equal to xj prime. Instead of ji prime, I can write xi jk prime, xi prime jk prime, take its derivative with respect to xk dv prime. Since the divergence of j is 0, that derivative just gives me ji. Now I can write this as del over del xk x j prime xi prime jk prime minus integral, no, the integral is outside, minus derivative of xj prime by del xk xi prime jk prime. Again, the first term I can just convert it into a surface integral which vanishes. I'm left with the second one. And the second one just gives me minus, well, that derivative is nothing but Kronecker delta jk xi prime jk prime dv prime, or xj prime ji prime dv prime. This is equal to minus xi prime jk prime dv prime. Okay, this is one identity I have. Basically, take j, multiply it with the, take one component of j, multiply it with another component of x, and if you just integrate over the whole volume, if you change the order of, no, sorry, this is j, order of the indices, you get a minus sign. That is the difference between the, no, this is j, the left-hand side and the right-hand side. Left-hand side is, if you just exchange the indices, you get the right-hand side, but it also changes the sign. Now let's go back. This we will be using it over here. Now I will be using this trick, r cross r prime cross j prime. This is equal to r prime times r dot j prime. Now, minus j prime r dot r prime, or r dot r prime times j prime. This is equal to r prime times r dot j prime minus r cross r prime cross j prime. So if you look at, for example, r dot r prime, multiply with j prime, integrate over r volume V, this is equal to r prime r dot j prime minus integrate over V minus r cross r prime cross j prime integrate over V. Well, the last term is kind of has the form that we are actually looking for, so we have to do something about the first integral. Now let me look at the j component of the first integral. Now the j component of the first integral is xj prime xi ji prime dv. Well, xi I can just take it out. What remains is xj prime ji prime dv. I can exchange I and j with a minus sign. This is equal to minus xi prime jj prime dv prime. But this is nothing but minus r dot r prime j dv prime, the j component. So basically this tells me that r dot r prime j prime dv prime, this is equal to minus r dot r prime j times dv prime. That is the first term on the right hand side in the first line, minus r cross r prime cross j prime dv. Well, just move the first term on the right hand side to the left hand side. They're equal. So eventually we obtain r dot r prime j prime dv prime. This is equal to minus 1 over 2 integral of, or r cross the integral of r prime cross j prime dv prime. Or going back to our vector potential A at the point R, remember this was 1 over r cubed, r dot r prime j prime dv prime. Now we know that this is now 1 over c times r cubed. We know that this is 1 minus 1 over 2c r cubed, r cross r prime cross j prime dv prime. And this is actually, we define this as mu cross r over r cubed, where mu is equal to r prime cross j prime dv prime times 1 over 2c. Now, we also simplified it to a better known example that you are probably more familiar with. This is just loop in a plane. Now, you see this expression is valid whether your current lies on a plane or not. This is always true, how we define the magnetic dipole moment. Now, for a loop in a plane, let's take our origin to be somewhere over there. This is our r vector. This is our dl. Mu would be 1 over 2c r prime cross dl prime for a current carrying wire, because just remember this recipe always holds. J prime vector times dV prime. If the J prime is confined along a wire only, this is equal to I times dl. If it is confined over a surface J, then this is the surface current density, let's say is K times ds. So this is mu in the case of a current carrying wire. But you see, this is, if you have this vector and this vector, let's say this is A, this is B. Let's consider this triangle. Or we can even consider this triangle. So this is the vector A. The area of any of these two triangles we have, this one and this triangle. Both triangles have the same base, they have the same height, so they have the same area. So the area will be equal to the magnitude of A cross B. So you see, considering this area over here, yes, 1 over 2. 1 over 2 times A cross B. So let's just look at this small triangle over there. R prime cross dl prime over 2 is nothing but, if you just assume this to be the n direction, this factor is nothing but that, let's say this is dA in the n direction. So that vector R prime cross dl over 2 has the magnitude of the area of that triangle, and it is in the direction perpendicular to the plane of this loop. Then the perpendicular direction you determine again by the right-hand rule. Just curl your fingers in the direction of the current and your thumb points in the direction of n. So mu in this configuration for this special case of a single current carrying wire is nothing but mu is equal to 1 over c times the area in the n direction. For a loop of arbitrary shape, not necessarily lying on a plane, this will be again true. Yeah, actually what you are actually doing here is that even if you have an arbitrary volume current density, you can just think of it as running in wires of some arbitrary shape. Many wires, they fill your volume. Wherever there is a current, you can imagine a wire. And you can imagine some segments of this wire. And if the segments are sufficiently small, they will lie on a plane. They will be straight, they will be lying on a plane. And that plane contains your line and your whatever origin you choose. So the contribution of that small segment that you imagine to the magnetic dipole moment is still the area corresponding to that segment. In this case, this area, in the direction normal to that area. You see, just imagine any current in your region, any volume current density. Let's say you are assuming you are calculating the magnetic dipole moment relative to this origin, just like the electric dipole moment. Will the magnetic dipole moment depend on your origin?
Area doesn't depend. Area doesn't depend on our origin. So
you see, if you remember the electric dipole moment, we saw that electric dipole moment does depend on the origin in general. Only under one circumstance it doesn't depend on the choice of the origin. Do you remember what was the condition?
rotation
Well, let's review.
What powers cancel each other?
Origin dependence. Electric dipole moment. It is defined as R rho of R dV. If you change your origin, what you are actually doing is this will be equal to R price plus A rho of R plus A, right? This will be equal to R rho dV plus A rho dV. This will be the dipole moment corresponding to the old origin plus A times Q. So unless the total charge of your system is zero, your dipole moment will depend on the choice of your origin. The monopole moment should be zero for the dipole to be independent, the electric dipole to be independent of your choice of the origin. Well, we can basically do the same thing for the magnetic dipole moment. So let's see. We define the magnetic dipole moment as R cross J dV. Let's just shift. So this is R plus A cross J dV. This will be R cross J dV plus A cross J dV. This is the monopole term. But we already see that the monopole term in the magnetic multipole expansion is just zero. R cross J dV. So the magnetic dipole moment, since there are no magnetic charges, do not depend on the choice of the origin, because the monopole term is always zero. Now let's go back. So let's say, since it doesn't depend on the origin, I can just choose any origin I like. So let me just choose that origin over there. So there is a current running through here. I can just imagine this very small segment. And then there is this area. And the contribution of that very small and very thin segment to the magnetic dipole moment will be just the area times the current, the very small current running through that very thin and very small segment in the direction of the area vector, corresponding again to that very small segment. It is basically, so in that sense, this expression is nothing but generalization of this law. But the difference would be, for a general current density, not all the Ls will be in the same plane. Since not all these wires will be in the same plane, you cannot just take, you see what we did over here is we replaced R prime cross dl by dA in the n direction, and then I could take n out of the integral, because since my loop is in the plane, n is the same for all the Ls, I can take it out. What remains is the total area. But if my loop is not in the plane, or I have this complicated current density, in that case, the normal direction to the area will depend on where I am, which very small segment I am considering. So I cannot take it out. So there won't be a simple relation like the area times the normal vector. But nevertheless, conceptually at least, this expression is nothing but the area times the current expression, generalized to systems in which the current density doesn't lie in a plane and it doesn't run over a wire. Any questions?
Tam küremiz olsa etrafına kablo yasasak böyle. Bakım gönderdiğimizde sıfır manyetik momenta veriyoruz.
So,
Simetriden götürüyorum ben.
hold on. So you have a sphere, and you are wrapping this with wire. Yes? And there is a current running through it. Let's call it I. The magnetic dipole moment of this system will not be zero. Well, let's calculate the magnetic dipole moment of such a system. Now, I will be assuming, I will take this sphere with a uniform surface charge density, sigma uniform. It rotates with an angular velocity omega. Let's, just for simplicity, let's assume it's the constant angular velocity in this direction. This is the direction of omega. So what is the magnetic dipole moment of this system? So what do you propose? How should we proceed? Let's first proceed with the simpler derivation, which we can use in this case. So this is my circle. I will divide it into very small rings. I will just pick up one of them, this one, let's say. It corresponds to some angle d theta. Let's say it has a thickness dl. And let's say this angle over here is theta. And there is a contribution to the magnetic dipole moment. This is the direction of omega. From that ring, which I can write as I times di, let's say, times its area, dA. What is the normal direction in this case? What is the direction of the magnetic dipole moment? You say, take your right hand. The direction is given by the right hand rule. So that ring is rotating around omega. So the direction of the contribution to the total dipole moment of that segment is in the direction of omega. So let's say omega hat. This is the contribution to the magnetic dipole moment. So we have to calculate, no, this is not dl, sorry, dA, it's just area. The area is not small. The area is the area bounded by the loop, not the area of the loop itself. So what is A? Let's say it has a sphere R. A is equal to R, no. You see, that was the mistake I had. The A is not the that A is not the area of this very narrow strip. So I have this, my ring, it's the area of the ring. You see, if I have a current carrying wire, the magnetic dipole moment of this current carrying wire would be the current running in my wire multiplied by the area enclosed by this wire. In this case, I have a ring, so that A is the area enclosed by my ring, which is? It will be pi r squared, but the radius of the ring is r sine theta squared times pi. This is my A. Now, I need to calculate the current carried by this ring. For this current, I have to find the area of my ring. Not the area enclosed by my ring, but the area of my actual ring. My ring has a total circumference, 2 pi times r sine theta, and it has a thickness dl. So this is the total area of my ring. Now, the total total charge on my ring is just this area multiplied by the surface charge density. And all this current passes through a fixed point in a time 2 pi over omega. So this is my dI. So let's do some simplifications. So that d mu, the contribution to the magnetic dipole moment from this very small ring, will be equal to A is r sine theta squared times pi. The I is r sine theta sigma times omega dl. Or pi sigma omega r cubed sine cubed theta times dl in the omega hat direction. Or I can also write this as d mu is equal to pi sigma r cubed sine cubed theta dl multiplied with the omega vector. So omega times the omega hat gives me the omega vector. So the total magnetic dipole moment of this system would be just pi sigma r cubed sine cubed theta dl omega integrated over all my rings. I have to sum I have divided my sphere into infinitely many rings. This d mu bar is the contribution from one of them. To get the total magnetic dipole moment, I have to sum all of them. Now what remains is I have to relate L and theta, or dl and theta, somehow. So how should I do that? How are they related, L and theta? dl is the segment of the length of that arc, which is the angle d theta. So this is equal to pi sigma r to the 4 sine cube theta v theta in the omega direction, which is pi sigma r to the 4 in the omega direction sine theta 1 minus cosine squared theta v theta, which is now we can evaluate that integral. That integral is just cosine theta minus cosine cubed theta over 3 times minus 1. Theta goes from 0 to pi. Do you agree? Well, let's see, how did we define the theta? Why? Now, this is, you see, this is, the downward direction is theta is equal to 0. The upward direction is theta is equal to pi, not 2 pi. And for each theta, I'm taking the total ring. So I'm basically covering over all the sphere by taking theta from 0 to pi. This is theta is equal to pi. So this is equal to minus pi sigma RQ r to the 4 omega. When theta is equal to pi, cosine pi is minus 1 plus 1/3. And when theta is equal to 0, I get the minus this 1. I have to subtract that, so I just multiply by 2. So this is equal to 4/3 pi sigma r to the 4 omega. Well, that's it. This is equal to, let me write it in a slightly different form, 4 pi r squared times sigma times 1/3 r squared omega. Well, the first term is the total charge. What else do you know that is proportional to omega? Moment of inertia doesn't have a direction. Well, it's a tensor, but it's not a vector. But angular momentum. So let's also look at the angular momentum of this system. You see, omega is not always easy to measure. But angular momentum will be kind of easier to measure because we know it is conserved. Again, I will just look at that ring only. What is the contribution to the angular momentum of that ring? Well, in general, the L is equal to R cross P. I have this ring that is rotating in this sense. If you just pick a very small segment, this will be, dl will be just di times omega, I omega. If you would just add the contribution from each one of the bits making the ring, this is what you would obtain. And this di would be just dm, the mass of that very small ring, multiplied with r squared, or r sine theta squared, multiplied by omega. R sine theta is the distance of each one of the masses on the ring from the rotation axis. Well, dm would be just 2 pi r sine theta. This is the circumference of the ring, multiplied by dl. This is the area of the ring. Let's just call the surface mass density as sigma m. This is the surface mass density. This is the total dm. So the contribution to the angular momentum of the sphere from that ring is just 2 pi r sine theta dl sigma m. This is dm multiplied with r sine theta squared times omega. Let's go back to the contribution to mu from that ring. They almost have the same functional form. So d mu would be, well, here I have a pi, in the L I have a factor of 2, so I will be writing the proportionality constant. I have to divide the L by 2. R sine theta's cubes are common. The L's are common. So this is my omega vector now, omega multiplied with omega hat. This is omega vector, they are common. The only difference is sigma m. In the L I have sigma m, in the mu I have sigma. So it's sigma over sigma m. Or this is equal to the L, since I'm assuming that the surface charge density and the surface mass density, they are homogeneous. This is nothing but Q over 2m. This is the contribution from this ring on the surface. And in fact, I can just integrate both sides. So the magnetic dipole moment of this object is equal to its charge divided by twice its mass multiplied by its angular momentum. And this relation you will also use in quantum mechanics when you are studying the hydrogen atom. The electron is orbiting the nuclei, it has an angular momentum, and it has a corresponding magnetic dipole moment given by this expression. And L in that case, the angular momentum will be some integer multiple of h bar. And this h bar over 2m is called the Bohr magneton. It's the unit of the quantum of magnetic dipole moment for an electron orbiting the nuclei. Or in fact, it's the quantum of, for a given particle, it can have an arbitrary m, it's the quantum of the magnetic dipole moment. Well, let's see, this is the z component. Now, the electron doesn't only have the orbital angular momentum, but it also has the spin angular momentum. So there is a corresponding to the spin angular momentum, there is a similar factor due to its spin. It's again Q over 2m for a given particle that has a spin. The magnetic dipole moment correspond to the spin is also given by Q over 2m multiplied by its spin. But spin is not the conventional angular momentum. So it's not, there's not a one-to-one correspondence. There's a correction factor G. So this G is called the gyromagnetic ratio. And for fermions, have you studied the fermions yet? Okay, you took quantum physics. Okay, you will see these. So it is some kind of early information. Now you will see that you have seen the spin, right? You have seen the angular momentum. This much should already make sense. The expression in rectangle is classical physics from your first year, even. So spin, you have already taken 300 quantum physics. You should have discussed that the electron has this property called the spin. You haven't heard of spin? Yeah, you have probably heard of it, yes. Yeah, I mean, not studied in detail, but come on, you have heard of the spin.
I can't define it.
Hmm?
I can't define it.
Nobody can. It just exists for some reason. So let's say for electrons, G turns out to be 2. Now we can calculate it, etc. It's not exactly 2. If you calculate the quantum corrections, it deviates slightly from the 2, and in fact it was the first calculation of how much it deviates from 2 earned the Nobel Prize to Schwinger. You will always see G minus 2. Because G for an electron has to be 2 without any quantum corrections, and with corrections it deviates from 2. Those deviations are small, so you just calculate the deviation from the 2. And that was, I don't know the year now, it was a Nobel Prize for Schwinger. So the things that you need to remember. Okay, this is basically how you can calculate the magnetic dipole moment. You just divide this one way. This is the way you could have done in first year. You have your large system divided into smaller systems that you are already familiar with, like the ring. You already know how to calculate the magnetic dipole moment of the ring. We divide it into very small rings, a collection of rings, and we then calculated the magnetic dipole moment of each one of those rings, because a ring is nothing but a current-carrying loop on a plane. And for such a system, the magnetic dipole moment is just the area times the current in the direction given by the right-hand rule. So we just have the mu is the contribution from one ring, and then to calculate mu, you just sum them up, which is nothing but your integral. You just integrate it. There was this interesting observation that the contribution from one ring to the magnetic dipole moment was very similar to the contribution of that same ring to the total angular momentum of the system. So we saw that that was actually indeed the case, with a proportionality constant that is independent of my ring. You see, the proportionality constant depends only on the surface charge density and the surface mass density, both of which we assume to be uniform. So since the coefficient is independent of which ring we are studying, we can just take the sum over all the rings. That would give me the total magnetic dipole moment in terms of the total angular momentum of the system. And in general, the magnetic dipole moment of a system can be written as in terms of its angular momentum. Of course, as long as the sigma over sigma m ratio should be constant, as long as that ratio is constant in a given system, this will always hold. It doesn't really have to be a sphere. The crucial thing would be this sigma over sigma m ratio. And this is actually the case even for the spin angular momentum that you will study later on, with some correction factor. So for an electron orbiting the hydrogen, you will see that the total magnetic dipole moment would be Q over 2m times L plus 2s. Well, this you will see next year, probably. Now, questions? Do you want a break? Maybe a 5-minute break. Because now we will continue with, okay, we know how, what's the vector potential corresponding to a localized charge distribution, like the atom, for example. You can use this in an atom. The next thing will be, if you take an atom, put it in a magnetic field, what happens? So what will be the force acting on this atom, what will be the torque acting on this atom, etc.